we will be performing regression analysis with multiple variables. Now the first part, we're going to work with the cars data set and saying the buyers of cars are interested in determining the factors which influence the car mileage in the city. So we're going to build a model first in regards to identifying what significantly impacts a car's mileage in the city. After that, we'll move to part 2, the Boston data set. And this consists of variables to predict pricing of housing. So a developer wants to know the factors which influence the pricing of houses. What models predict or influence housing prices? So, as always, we start off with our working directory. So you want to set that working directory to wherever your CSV file is saved. We go ahead and run that. We get working directory to verify. Perfect. Now, let's call our data frame within R cars data. And let's read in the CSV file called cars.csv. Okay. Now, we assume that's been read in because it shows here that there's 420 observations of 15 variables with a data frame in the environment called cars_data. To verify, we can go to the view command with cars_data, which will open this here. Shows we have make, model, type, origin, drivetrain, MSRP, invoice, engine size, cylinders, horsepower, miles per gallon in the city and on the highway, the car's weight, its wheelbase, and its length. So that's all in there. We can verify the structure of that car's data. But actually, before we do that, how about we take a look at the summary statistics of that car's data frame. We see here we have a number of different makes of cars, a number of models of cars, 6 types of cars, 3 origins, 3 drivetrain types, over 400 MSRP unique counts, over 400 unique invoice counts, and then we have variables with min, median, mean, and max. If we run the structure, it should support that. So we see make has 38 factors or levels, model has 425 levels, type is 6, origin is 3, drivetrain 3, MSRP and invoice 410 and 425, and then we have numeric and integers for the rest of the data. So if we want to build a data set, let's call the results of that linear model cars_results, and we'll specify that we want a linear model run. The formula is equal to MPG city because that's what we're trying to predict. Now, what variables do we want to include in the model? Well, ideally we'd want to include all of them, but when you have too many levels within a factor, it can't group appropriately, and so it would hyper bias towards the model or to the training set. So we're going to ignore make and model, MSRP, and invoice. So we want to include type, use the plus sign for additional variables. We want the origin, so 6 levels, 3 levels. We want drivetrain, which also has 3 levels. We want engine size. We want cylinders. We want horsepower. Now, one of the things we're actually not going to include is miles per gallon in the highway. If you've ever heard of something called multiclinearity, it's the thought or assumption that predictors that are highly correlated can influence one another and reduce the significance of each one in the model. In addition, because a car's miles per gallon in the city is likely tied or correlated extremely highway with miles per gallon on the highway, we don't want to bias the model. We want to understand what features are actually driving a high miles per gallon. So we had horsepower. We can use the enter command to drop down a line. We want to add weight, wheelbase, and length. And this is all coming from the data set called cars_data. So if we run this model, it's been run. So first we can type cars.results to see the weights of each of the variables in the model. So you see, other than the intercept, we have type that was broken down in this model. We have the origins broken down. We have the drivetrains broken down. And then the rest are single counts because they were numeric and integer, whereas these others were factors. Now, we actually want to look at the impact of these variables on the model. So we use the summary command to look at CAR's results. Now, if we scroll up here, we can see we have the function that was called, and now we have the coefficients. Again, the intercept isn't as important, but we want to look at the significance and significance levels of the other types. So, it seems like the type of vehicle largely impacts the miles per gallon in the city. It looks like the origin is significant at 0.1, but if we're doing a 0.05 significance level, which is very common, then origin is basically not significant to this model. Drivetrain is significant, at least for the front, but considering it's front versus rear, that's fine leaving both in the model. It appears engine size, p-value of 0.44, obviously not below 0.05, is not significant to the model, as verified by a lack of asterisks. Cylinders, 0.34, is not less than 0.05, also not significant to the model. And then it looks like horsepower, weight, wheelbase, and length are significant to the model. We see that the residual standard error is 2.09 with 410 degrees of freedom. 2 observations were deleted due to missingness of data, so R automatically did that. We have our multiple R squared, and based on the sample size as well as number of variables in the model, we have our adjusted R squared. So we're 84.14% confident in the accuracy of our model, leveraging the significant variables for predicting miles per gallon in the city. And we see our p-value is significant below even 0.001, 2.2 with 16 decimal places of zeros. So that's our CARS data set. We can use Control L to clear this workspace. And let's go further now. So here we'll work on our Boston data set. Now, we've already specified our working directory, so we can go to Boston data, read.csv, boston.csv. We run that. It looks like it ran, and over here, Boston data, 506 observations with 15 variables. So we'll repeat what we did before as well. We want to view the data set to make sure everything looks okay. Looks like everything is numeric or integer and got loaded properly. We want to do a summary of the data. And we want to look at things like making sure there's no negative values. Now, the Boston data set you can Google is available on Kaggle in regards to the data dictionary. So, when we're looking at these variables at the top, CRIMs is the per capita crime rate per town. ZN is the proportion of residential land zone for lots over 25,000 square feet. Indus is the proportion of non-retail business acres per town. CHAS is whether the Charles River, encoded as a dummy variable, 1 if it tracked Browns the river and 0 otherwise. NOx is the nitrogen oxide concentration in the parts per 10 million. RM is the average number of rooms per dwelling. Age is the proportion of owner-occupied units built prior to 1940. DIS is the weighted mean of distances to 5 Boston employment centers. RAD is the index of accessibility to radial highways. Tax is the full value property tax rate per $10,000. PT ratio is the pupil to teacher ratio by town. Black is a computation proportion of blacks per town out of 1,000. LSTAT is the lower status of the population in percentage. And MEDV is the median value of owner-occupied homes in thousands of dollars. So you can see it's a lower number here to make it easier to work with. So we have the summary. We can review these values. And we also want to look at the structure of the data to make sure it was ingested correct and we can work with it. So all of these are integers and numbers, so we can obviously work with them. Now, there's a neat trick within R where instead of you having to type up 15 variables, and now 15 is obviously not a lot, but let's say you're working with hundreds of variables, you might not want to manually type all of those variables out. So what we could do is build a linear model. We use the LM function again. We say the formula, and we're trying to predict that median value of houses. And we want to include all variables. So instead of typing every single variable, we can use a period here. Then we say data equals Boston underscore data. We run that now. We go ahead and look at the coefficients, and we can see all these are in here. And then we want to look at the actual results of that model. We look at the call. We see X, which seems to just be the number 1 starting with 506, as not significant. We could have technically removed it from the model, and instead of a plus sign, we could have used a minus sign. Now, we want to look at these other aspects of significance. So, crime is 0.001, so that's significant. So crime affects housing prices. ZN, that proportion residential land zone, 0.000, so that's significant. Non-retail business acres, 0.745, that's not significant. So it's not important to the model in regards to predicting housing prices. CHAS, whether there's the river nearby, is significant. Whether there's low or high nitrogen, oxygen, or nitrous oxide concentration is significant. The number of rooms is significant. And mind you, significance is purely based on cutoffs, whether there is or not. However, from a visual perspective, you can see that rooms is extremely significant because we can't technically use the term in statistics extremely significant because, again, it's basically binary of significant or not significant. But this model has 16 zeros after the decimal before it hits 2. So rooms are extremely important, at least, to predicting housing prices. Houses built prior to 1940, not significant, 0.884. And then it looks like the remainder of the variables are significant to the model. We again get the degrees of freedom. We get an adjusted R squared of 0.734. So our model fit to new data will likely be accurate 73.4% of the time. We're 73.4% confident in this model's ability to predict housing prices. And then the overall model, instead of the individual coefficients, the overall model has a p-value of 2.2 e to the negative 16th power, which means the overall model is significant below a 0.05 level. Technically below a 0.001 level, but at 0.05 the overall model is significant. So we can say that based on the variables input into the model, we are confident that our predictions in regards to housing prices are not due to chance.